Well, instead of having one point y, we have k points that give me a k plane. So these are the k vectors whose span give me a k plane, and k plus this capital I runs from 1 to k plus m. This runs from 1 to k. And I say that these guys are a positive combination of positive external data. But now this positive has to be acted on by k linear transformations. These numbers, these coefficients are a k by n matrix. And so their notion of positivity, we use that as a positive restaurant. And so this gives me a region, like a polygon, the analog of a polygon, but now this lives in GK k plus 4, GK k plus m in general. Which is the projection, you think of it as a projection of the positive external data, the projection of the positive Riemannian through this external data set. That's a region inside GK k plus m. And as I said, remarkably, the canonical form associated with that region is the amplitude. Okay? And if you want to, if you take in that C, if you go down to particular low-dimensional cells in the positive Riemannian, then that will light up certain parts in Y space. Okay? So those combinations, those cells of the positive Riemannian that added up, the rule that tells you how they should add up, the new rule, the intrinsic, the new mathematical rule, making no mention of space-time locality in the right answer, is just triangulate the amplituhedron. Okay? And you don't even have to do it that way if you don't want. The amplituhedron is the answer to the question. Anyway, there's a generalization of this to all loop order. I won't have any time to explain it, but I want to say the canonical form of the scattering amplitude. From this definition, you can see in various degrees of completeness, but certainly many examples very concretely, just from this definition directly, how the boundaries of the amplituhedron manifest this property. That is, go to the boundary, it factorizes into lower pieces in a way that's exactly what it's supposed to do to reflect locality and precarity. And finally, there's a very obvious symmetry of the amplituhedron, which is that you can do any diffeomorphisms on the space that do anything you want on the inside, but leave the boundaries invariant. So you can call these positive diffeomorphisms. If you track through what the generator of positive diffeomorphisms is, it's the Yangian symmetry on the nose. Okay. So this mysterious infinite dimensional symmetry is very obvious in the Riemannian amplitude. Okay, so all those things that I mentioned, you should hope to see are things that, at least in this example, we could see.
So diffeomorphisms that you want, or it's some piecewise linear?
Yeah. So I don't know what the official word is, but it's any motions on the inside that leave the boundary space. Okay. And just to give you a concrete example of the kind of geometry problem that's involved, this is the problem that you have to solve. This is the space you have to understand and triangulate. If, let's say, for 4 particle amplitudes in this maximally supersymmetric theory, you want to calculate L loop amplitude. So here's the geometry problem. In a 2-dimensional plane, look at the upper quadrant. Populate the upper quadrant with red points and green points, anywhere in the upper quadrant, simply with the property that for any pair, AI minus AJ dot BI minus BJ is negative. So the line from I to J points in the opposite direction for the A's and for the B's. That's it. Understand that space. Understand means triangulate it, cover it with a nice set of coordinates, really understand it. Okay? Triangulate the space. The triangulation of that space directly calculates the L loop amplitude, or the so-called integrand for the L loop amplitude. And while we have not solved this high school geometry problem, or at least posable to a high school student geometry problem, we've solved it in special enough cases to allow some first computations in this theory of non-trivial results for any number of particles, any number of loops. Okay, so, okay, all right. So you guys have been incredibly generous with your patience. So I'll wrap up. In this example, we can see that the amplitude is the canonical form of the amplituhedron. Once again, there's the space that sits there. There's a nice way, a nice class of ways of breaking it up into pieces, each one of which is associated with one of these on-shell diagrams. You can do it in any way. The pieces don't have space-time or quantum mechanics interpretation, but only the full volume does. And I think the most conceptually interesting thing is that the rules of space-time and quantum mechanics really emerge as derivative notions from this positive geometry. Okay. So, and I won't have time to talk about any of the rest of this, but there's been a number of developments just in the past year or two that I think are conceptually quite interesting. There are much more intrinsic and invariant and more topological and combinatorial ways of talking about this amplituhedron, very different than what I told you.
Are these slides in your homepage?
Somewhere, yes. Yeah, I'll try to put them. Yeah. But anyway, if we go back to this question I was asking you, part of the novelty of the things that I haven't talked about, see, what I told you here is this amplituhedron still lives in some auxiliary space, some auxiliary Grassmannian space. In the last year and a half in the work with Hugh Thomas, we've seen how to see that this amplituhedron really lives directly in the configuration space, directly in that space of 4 by n matrices that defines the scattering problem. Okay? There's a sort of simple projection that relates one to the other, and there's a more topological way of characterizing the amplituhedron in terms of winding numbers and signs of patterns and so on that really directly defines it in the space that it wants to live. And so in all these examples, the answer to this question of what breathes physics life into the seemingly arid space of this 4 by n matrices is with the, as I said, the frisson of some structure added, like the word ordering, the word positivity, that puts enough structure to allow a large amount of non-trivial things to come out, which have the non-triviality of the richest complexity we need for scattering. So in all of our examples, in this seemingly arid space, with a little bit of structure of the combinatorics, positive geometry, and the canonical forms and so forth. Okay, so that's all. This is an example, in this baby example, and very, very far, long, long way to go, but you also see in this example this ideology that I was advocating or hoping for. We see space-time, the rules of space-time and quantum mechanics are attached to each other, right? Space-time and quantum mechanics are about what happens on the boundaries of this space. And so it's not two very different things. It's just there is a space, you go on the boundaries. The boundaries are of a special kind, and it factorizes on the So the space-time and quantum mechanical interpretation are a direct consequence, are possible to separate from each other. Anyway, I've been having an enormous amount of fun in this subject. To me, it's an exhilarating adventure. And one of the things that I really enjoyed, I mean, in the interaction between physicists and mathematicians, sort of historically, there have been many periods when the mathematicians were, decades ahead. Like Riemann had Riemann in geometry sitting there, and then physicists use it. Or Galois had group theory, and physicists use it 100 years later. Sometimes it's the other way around, where physicists have the apparatus of the path integral, and they have all this intuition for what quantum field theory does, and they produce amazing results. So the physicists are ahead, and the mathematicians have to catch up and figure out what it means. And this subject is exactly not like that. One of the most wonderful things about it is that, especially when we first ran into these objects, we realized that there are mathematicians who are also running into them at basically the same time, slightly earlier to begin with, and then, but we have complementary pieces of intuition about it. We're learning from each other. We're actually working together, and not just one person telling another person, I have this conjecture, you go prove it, but we're actually jointly working together to try to figure this out. So to me, it's really exhilarating and tremendous fun. By the fact that I've gone over so long without giving you any kind of complete picture of anything, it's clear there's no grand synthesis yet. But I hope there's a grand synthesis yet to come, and if there is, I hope whoever finds it comes and gives you a proper 1 hour to look at it.